Okay, so hopefully you all can hear me. Hi. So I wanted to talk today about a specific category of the dangers that we were just talking about with that previous talk, right? So I'm focused specifically on the possibility for machine learning algorithms, and like the previous speaker, I'm not going to be talking about AI, right? But specifically machine learning algorithms, and the ways that they're now being used in society in ways that may be harmful to society. So there have been a number of news reports now going back, this is from 2015, which is right about when sort of the popular understanding of this problem started. So machine learning algorithms are now being used to help companies hire, usually as an initial stage in the hiring process to determine who should receive an interview. They're also being used to do predictive policing. And closer to here, there's discussion about using them to determine who should be released without bail and who should be detained pre-trial in Philadelphia to try to relieve overcrowded jails. And this type of thing is in fact also happening nationwide, both pre-trial and at sentencing time and at parole. This rise in the use of algorithms in society has also led to a corresponding rise in the concern over their use in society. This includes a case that made its way to the Wisconsin Supreme Court, where a defendant challenged the use of an algorithm to try to determine their sentence on the grounds that this was a proprietary algorithm, and so they weren't being given the opportunity to face their accuser. Again, closer to home, there have been city council meetings in Philadelphia saying, you know, if you're going to consider instituting an algorithm that might have some impact on whether someone is released or detained, then we should consider whether that algorithm is racist. And a similar question has been raised in Chicago over the use of predictive policing in that city. And all of this has led to pretty prominent calls for more accountability for big data algorithms, for these machine learning algorithms. And really what I'm going to be talking about today is one form of that accountability, or how, if we were trying to do our best, how we could try to identify potential problems in the implementation of these algorithms. And as part of that end, as was mentioned in the introduction, I'm one of the co-founders of an interdisciplinary conference that looks at these questions. So computer scientists, policymakers, lawyers, social scientists, and so on come together to discuss these issues. So if you're interested in learning more, this is one place to learn more. Okay, so the question for this talk really is, how does discrimination enter algorithmic decision making, and what can we do about it? And mostly I'm going to talk about work that I did on thinking about a potential series of traps that you could fall into. And this is joint work with my wonderful colleagues shown here on one of our Skype calls. As one of my colleagues likes to point out, this could be seen as the answer to a joke about two computer scientists, two sociologists, and a lawyer walking into a bar. Because this really began with some heated debates among the five of us about how these algorithms should be implemented and where it was appropriate and where it wasn't. And eventually we managed to reduce this to a series of traps. All of these traps center around the idea of abstraction in computer science. And abstraction is, one might say, the most fundamental concept in the field. And this is really what gives computer science, and especially machine learning, a lot of its power, is our ability to nicely formulate a problem, encapsulate it, and make it reusable in lots of different scenarios, right? And this is why we're able to talk about machine learning as applying to hiring and the criminal justice system and medical decisions, right? Is because in fact we're able to abstract away the specific scenario and apply the same algorithms across all of these different domains. And so this is, computer scientists think about this as being elegant, right? This is a really beautiful idea, but it's also a problem. Right? And what we're claiming here is that it's a problem because it encourages exactly this reuse, and it strips away the context. But of course, we might imagine that the criminal justice system and the medical system have different needs, right? And that maybe there should be different assumptions baked into the algorithms when used in these different contexts, right? So how can we identify those traps we might fall into, these traps of abstraction? So the first one I'm going to talk about we call the framing trap. And this is essentially when you are making that first definition of the problem, when you're defining your boundaries, right, your frame around the problem that you're going to consider, do you even put them in the right place? Right? So that's the first trap. And how might this work? So I want to also use this opportunity to really give you a little bit more of a detailed sense of how some of these algorithms work. So here's a hypothetical case study. So I should say I've never worked for Facebook. I have no idea how any of their algorithms work. This is purely hypothetical. But one of the things that Facebook has repeatedly come under fire for over the years is the requirement that everyone on the site use their real name. And I'm going to assume that there's not a bunch of people sitting around looking at every name that's typed into Facebook, but rather some of this screening to determine if you are using your real name on Facebook happens algorithmically. And so specifically, this is Dana Lone Hill, and she was part of a group of Native Americans who were raising the issue to Facebook because many of them who were using their real names had been rejected from Facebook for not using their real names. Right? So they were raising this issue saying, you know, your algorithm or whatever you're doing doesn't seem to work, and it doesn't seem to work and it's targeting our community specifically. So how might this have happened, right? So here I'm going to collect a bunch of data about people, right? So I'm going to collect the names, and then I'll also collect some attributes about those people, right, and about those names. So I might decide to find out, okay, is this a top 1,000 baby name? Is some part of this name in the dictionary? And then I will go ahead and collect information about whether this is a real name or not. We could think of these as outcomes or labels. They carry a bunch of names for this. But essentially, we imagine that this is some ground truth information about the realness of this person's name, right? So Sorelle is my real name, Lady Gaga is not her real name, and so on, okay? So we do this, and then from this data, we try to determine what pattern might emerge, and we make a model or a classifier based on this pattern. So if you look at this for a minute, and you were going to make some simple rule based on the data that we have here, maybe you would come up with this rule, right? So maybe you would say, okay, if the answer to is it a dictionary word is yes, then I'm going to say no, it's not a real name, right? So that's one simple pattern that you could come up with from this specific data, which is known as the training data. You could make yourself a classifier, and then along comes Dana Lone Hill, and you would put her into your data, and you would say, okay, based on this model that I've made off of my training data, is that a real name or not, right? And you would say, no, it's not a real name. Okay, so obviously this is sort of a toy example, but hopefully it gives us some ideas of what might go wrong in these systems, right? So the systems are very much based on the specific training data that you used to try to develop your model. And different subpopulations might have different observed properties in the training data, right? And so if you fit a pattern to the people who are in the training data and then you apply them to people who were not in the training data, right, you might not do so well. The other issue is that minority populations are also numerically often a minority in the data, right? And so if what we're doing is looking at a common notion of machine learning accuracy, right? If you were looking at accuracy, then essentially the way that accuracy is scored is that each person in your data set is worth 1 point, right? And so Native Americans represent about 2% of the US population. So if they were represented proportionally in your training data set, and you incorrectly classified all of the Native Americans in your training data set, you would have an accuracy of 98%, imagining you got everybody else right. And you would look at that 98% number and you would say, you know, I think I did pretty well. 98%, that's pretty good, right? But what you would have missed out on is that you had gotten 0% of the Native American subpopulation right? And so probably you should have also evaluated your algorithm on that specific subpopulation, which would have allowed you to know that actually you weren't doing very well, right? Okay, so I also think a lot about the use of these algorithms in the criminal justice setting, so specifically risk assessments and predictive policing. And so I wanted to talk you through one of the really prominent examples of this that's come up there. So this was a really groundbreaking study by some folks at ProPublica from a couple of years ago, from 2016. And they collected data from Florida, from Broward County, about the use of an algorithm that's used nationwide, and the algorithm is called Compass. And the way that these risk assessments work is that people fill out this sort of survey. So when you're being arrested, someone will fill out a bunch of information. Maybe they'll ask you some additional questions. They'll compile information about your criminal history. All of that will go into what's known as a risk assessment. In this case, the algorithm is called Compass. And out will come a score, right? And this is just like out came the prediction about the real name. In this case, you get a score. And the specific version of this that I'll be talking about is that second red bar, the recidivism score. And so this is essentially the risk likelihood that the person will recommit a crime if you let them go. At least that is what it is supposed to be measuring, right? And that is what it is sold as measuring. And then in this case, it'll also give you some additional set of characteristics and needs. So this is what the output looks like from the algorithm. And what the folks at ProPublica found when they compiled the data that they'd received about lots of different people and their scores, and then when they followed those people for 2 years to see if they were rearrested, what they found is that the prediction succeeded in a similar way across both white and black populations. But when it failed very differently, right? In a way that represented some amount of bias. And the issue that they found was essentially that white defendants were given the benefit of the doubt, right? So white defendants who who went on to reoffend were more likely to be labeled lower risk, right? They got the benefit of the doubt. And for black defendants, it worked the other way around, right? So black defendants who didn't go on to reoffend were more likely to be labeled higher risk, right? And you'll notice here that they were more likely to be labeled higher risk by a lot, right? Almost twice as likely. Okay, so this story came out, and ProPublica not only gathered this data and released this story, they also released the data and they released all of their analyses, right? It was a really good example of full transparency. And so it spurred a lot of double and triple checking of their work, and it spurred a lot of further work on this in the community. And essentially there's been a lot of discussion about what went wrong. And so there's a couple of things. So again, different subpopulations have different observed properties. And the observed data used to train and assess model outcomes may be biased. And there's a specific way that this particular data may not be telling us the full story. And this is not specific to ProPublica's analysis. This is actually the way that most of these risk assessments are analyzed, right? Are trained and are analyzed. The idea is that you want to find out whether someone will recommit a crime. But what actually happens is that you check to see if in the next 2 years they're rearrested, right? Now, arrest is not the same as conviction, and conviction is not the same necessarily as having committed the crime, right? There might be people who committed crimes who were never arrested and never convicted, and so on, right? And the issue is that this also leaves in some avenues for bias, right? If the police are heavily policing certain neighborhoods and are more likely to arrest people there, then it will look like those populations are more likely to reoffend. But in fact, what you are finding is just your measurement bias. And so, again, I said, they've released all of their data. This has spurred a lot of work in the computer science community, specifically in the community focused on fair machine learning. And some of that work has focused on, okay, if I'm given this data, then how can I try to at least equalize the error rates, right? So remember I said essentially white defendants were given the benefit of the doubt. How can I make it actually so that everyone's given the benefit of the doubt, or at least equalize the extent to which that's true? So some people have focused on creating algorithms to do that, and others have focused on noticing the tension between wanting equality of accuracy and wanting equality of error rates. And essentially there's a couple of reasonable definitions of fairness, and you can't satisfy all of them if you're in this situation where the base rates of rearrest are so drastically different, right? So essentially that difference is in the data, and it has to go somewhere. You can't just sort of magic it away, right? These machine learning algorithms are trying to understand the patterns of the data, and if that's a pattern in the data that you collected, then you're going to have a fairness problem. And so, from my perspective, that represents a failure under this framing trap, right? Because you've assumed that your data is correct as is, and you've moved forward to try to model it that way. And in all of this, we've left out the actual process, right? So it is not actually the case that these risk assessments themselves decide who is detained and who is released. What actually happens is that these scores are given to a judge, and then the judge takes that into account or doesn't, right? So in fact, we could have a long conversation about whether the risk assessment itself is fair, right? Whether it's doing a good job of capturing the notion of risk, but the judge might say, you know, these tools, I don't like them, right? And then all of this nuanced conversation goes out the window, right? So if we don't think about it actually in the context, then we're not really getting anywhere. And there's a field called Science and Technology Studies. This is the field of two of my co-authors. And for them, this is just obvious, right? Because they understand all technology as being rooted in a socio-technical system, being rooted in society by all of us who use it. And they recognize that if you look at what's happened when you've adopted technology in the past, it'll tell you something about how it's going to go this time and the various things that you should pay attention to. And one of the ideas that's come out of that community is that you should always think about humans as being part of the system, right? You can't think about the technology as being fully separate from the humans. And one of the classic examples there is the cell phone, right? So we think about the cell phone as being just an object, but if you don't pay for your service, which is sort of a human action, it won't work. But also if you take it to somewhere where there's no cell phone towers, it won't work. And if you have a cell phone that works on some particular type of cell phone towers, right, and you take it to a different system, like Europe, it also may not work there. And all of those systemic ideas that are in place are really human notions. Right? The cell phone works partially because of the technology, but partially because we've placed it in this system and made sure that the protocols allow it to work. So the next trap. We call this the portability trap. And this is essentially focused on the various ways that we might, say, abstract away a system and then just try to move it somewhere. And what happens when you do that. So for this, I want to talk a little bit more about predictive policing. So there's a number of different types of predictive policing. You can try to predict where to send the police. You could try to predict who to target for surveillance, right? Who you think might be about to commit a crime. Or you could try to predict who a victim of the crime might be so that you can protect them. And I'm going to be focused on that first one. So if we imagine that we have some historical data about crime in different neighborhoods, the goal is to build a model to predict how to allocate officers to these various areas. And there's at least 2 companies, many more, who are involved in doing this. HunchLab is actually based in Philadelphia. I'm going to look at PretPoll here. So PretPoll has taken the step of releasing a white paper, right? And so I guess the advantage for me of their transparency is now I can critique them. So this is essentially their model. This is a slightly simplified version. But in a specific location, they're trying to predict whether there's likely to be crime there tomorrow, based on whether there was crime there today, and then including some delay, right? So including some sort of decay in the importance of the of whether there was crime. And the idea behind it is that it's essentially an earthquake aftershock model, right? With the idea that perhaps criminals are likely to repeatedly come back to locations where they know that they've been successful. And I think that this raises a whole lot of questions, right? So does it make sense that we should use an earthquake aftershock model to predict crime, right? That feels like I understand how they were able to take this nice model, right? They abstracted away the context that used to be earthquakes, and they moved it into crime, right? But we should obviously be asking, does that make any sense? And we should also be asking, okay, so you've created a company, and presumably the goal of your company is not just to sell to one specific city, right? You probably want to be national, so you want to be able to take your model of predictive policing and sell it all over the country, in which case we should ask ourselves, okay, does this model that's being used in LA, which is where PretPoll is based, does that apply to New York? right? We might imagine that a city that's really based on a car infrastructure might be different than a city based on New York's public transit system, and that many other things might also be different based on density and types of neighborhoods, right? Can you really take this model and just move it to a different city and expect it to work? And the same question applies to these risk assessments. So often risk assessments are developed for use at sentencing time, right? To try to predict how long you should keep someone in prison so that when they're released, they're less likely to recommit. Well, often these things designed for sentencing time or some other specific scenario in the criminal justice system are then moved to a different scenario, right? So this thing at sentencing time might now be used for parole. But at parole, you've already completed some of your sentence, right? So what does that mean? Is it still telling you what you actually think that it's telling you, right? Or potentially what the company is selling you, right? And the same questions happen even when you then say, okay, I'm gonna try and make these systems fair, right? You're still gonna have the same issues of potentially not being able to just port a fair system from one to another. So some of the work that I've done is tried to think about what are the belief systems at play when we're trying to design fair algorithms. And my claim is that one of the things we're often doing is separating between our idealized notion of what's going on in terms of our training data and in terms of our outcomes versus the observed actual reality of the training data we are sending into the algorithm and the outcomes that we are able to observe and record. Right? And if the outcomes that we ideally are measuring, like reoffense, perfectly match the outcomes that we're trying to write down, that's a very different scenario than if they don't, right? So in a situation where we're thinking about loan repayment, while we can't see what happened for the people who we didn't give the loan to, we can see whether the people we decided to grant the loan actually repaid us back, right? And that's pretty observable accurately. On the other hand, we can't observe reoffense. And so if we take a system that's designed for loan repayment, even for fair loan repayment and loan allocation, and we transfer that into risk assessments, there's no reason to think that our assumptions will continue to hold, right? We actually need to go back and remodel things. And the science and technology studies theory that this relates to is called user scripts. So they have a notion that when you design a technology, that technology comes with a set of narratives about how it is and should be used. And so you should keep those narratives, those user scripts, together with the technology so that when you transfer it into a new context, it becomes very clear that it was never actually designed to handle that. And there are examples of this from the fair machine learning community already. So there have been a number of similar suggestions all around the same time in the past year or so of people saying, you know, we should really make model cards or data sheets. They come under various different names. But the idea behind all of them is that we should make something that says, you know, this is the specific training data. So for example, this is the specific city that this policing algorithm was designed on. Right? And therefore, these are the specific scenarios it was designed to be used under. And if you transfer it to some other city or some other set of contexts, we do not expect that it will work. Right? Next, we posit that there's also a formalism trap. And this one, I have to tell you, is really tough for computer scientists to be okay with. Because this is really the one that says it might be the case that you can't take a social phenomena like fairness and mathematize it, right? It might be the case that, you know, computer scientists are not the perfect people to solve this alone. And really, this all comes back to what does it mean to be fair, right? And what it means to be fair is potentially going to be different for all sorts of different people or animals. Right? And this is a notion that we as computer scientists reckon with regularly when we're trying to make something fair, right? And not to pick solely on other people, I will pick on my own previous work for a case where I have done this type of work. So there's a notion of disparate impact that comes out of US law. So there was a case in 1971, Griggs v. Duke Power, and the case was looking at Duke Power Company, which had historically refused to hire black workers, and now was no longer allowed to do that explicitly, right? And they said, aha, well, in the location that we're in, historically, black people in the community don't have a high school diploma, so we'll now just require a high school diploma, and then we can go on discriminating against black people, and it'll be facially neutral, right? And the Supreme Court said, no, you can't do that, right? That's a little too obvious, and you can't just directly use proxy variables. What's important is the outcome, right? However you pretend you are doing this process, if it has the outcome of discrimination, then that is discrimination. And that notion of discrimination is known as disparate impact. And the Equal Employment Opportunity Commission, the EEOC, has codified that into what's known as the Four-Fifths Rule. And the idea there is that if you are applying for a job, right, all people from different groups should have similar rates of being accepted to the job. Right? And ideally, this ratio would be 1. The two groups would have exactly the same rate, but we recognize that there may be some variation, and so they say, okay, as long as it's above 4/5, then we'll consider it fair. And if those two rates of receiving jobs from the different groups become drastically different, then we'll consider that you might have a problem, right? At which point the EEOC might open an investigation, try to determine if there's some business reason why this is happening, and so on. There's sort of a whole human process that kicks in at that point. Yeah, so this is just saying what I also said in words, but I'll tell you with the math a little bit more. So this is saying if the probability of receiving the job, so C equals 1 is like, yes, you got the job, given that you're in the minority group, divided by the probability of receiving the job, given that you're in the majority group, right? You want that to be big enough. In other words, you want these two probabilities to be roughly equal. So I did some work following up on this mathematical version, this idea of fairness in a mathematical way, that says, okay, suppose that I have some training data set, and I want to know that a company potentially using it for hiring is not going to make discriminatory decisions, but I don't know what algorithm they're going to be using, right? Is there some way for me to see if potentially a malicious actor could discriminate based on the data that I'm giving them? And the way of doing this is that you look at the ability, so say you're worried about discrimination based on gender, you would look at the ability to predict someone's gender based on all of the rest of the data. Right? This assumes here that the company is not going to try to explicitly discriminate based on gender. Right? It assumes that they're essentially a good actor, but there may be information about your gender encoded in the rest of the data that you gave them. Right? Maybe you went to an all-women's college or so on. And so if they can use that information to predict your gender with low error, then they could potentially end up discriminating against you based on it. And on the other hand, if they can't, no matter how hard they try, right, if they can't predict your gender with low error, then that data set is actually safe to use, right? Then if they use that data set, whatever machine learning algorithm they throw on it, it's not going to end up being biased based on gender. So this seems very nice, right? And then you wonder, okay, well, what if it was biased based on gender, right? What if there was pretty low error in predicting my gender? Then how would you get rid of it? And we proposed a way of doing this. So here, these are some hypothetical SAT scores that might be used to make a decision, right? And the red curve are the male scores, and the blue curve are the female scores. And the problem when you look at those is that they're separated, which means that they carry information about which gender these various people are in. And so you can do this trick where you move them both to that black distribution in the middle. It's formally a median under a certain space. So if you move them to that black distribution, then now both of those distributions are in the same place. You can't tell the difference, right? If you do this with your training data, and then you check to see how biased the results are, in fact, it'll turn out that even though the results for each 3 of these data sets sort of started in the biased region, they started on the left in that sort of red zone where the disparate impact was high, that gradually as you make this change to the data, you'll actually end up with decisions that are more fair. But here's where I pick on myself again, right? Because they're more fair under this specific mathematical notion of fairness, right? And there are a lot of things that that doesn't capture. So first off, many definitions of fairness are actually process-based and not outcome-based. Right? I set up my whole definition so that it was entirely outcome-based, right? Which ignores ideas of procedural fairness, of making sure that everyone had a fair shot in this job interview process, say. Again, it also, notions of fairness may depend on the context that they're being used in, right? So I'm imagining a hiring scenario where it might make sense to follow this EEOC guideline. There might be other scenarios where that is absolutely not the thing that makes sense. And it also doesn't allow the potential stakeholders involved to contest the decision. Right? There's many times where you might want to be able to say, you know, you just made that decision about me. You should have to tell me why, right? I should get to challenge that. And again, from an STS point of view, one of the important and potentially concerning things about what's happening in my research community in fairness and machine learning right now is that there's a period of time in research communities, so the STS scholars tell me, when definitions are still malleable. When you could say, okay, I'll try this definition of fairness or this one, where it hasn't yet solidified into a cultural norm about what we actually mean when we say that. And we're currently in that phase right now. And based on the history, what STS scholars advise is that you want that period of flexibility in the definitions to be as long as possible, right? Because at some point it'll solidify, and then it'll be very hard to get people to think actually carefully and in a nuanced, exploratory way about these definitions, because they'll see them as given. And that seems especially important with social constructs such as fairness, right? Why should we believe that as computer scientists, having looked at this problem for, say, 10 years, that we would be able to really understand fairness, when of course this is something that's been debated by philosophers for hundreds, if not thousands of years. So next is the ripple effects trap. And this is essentially the trap of not realizing that there might be a step after you introduce your technology, right? Where you introduce your technology and then society has a chance to respond to it. So going back to predictive policing again, and picking on PretPoll again. So there's a nice study that came out a couple of years ago now by Christian Lum and William Isaac. And what they did was they took PretPoll, they took that formula that I showed you earlier, and they fed it historical arrest data from the city of Oakland. And then they tried to see what happened when you ran that data back through. So you imagine that you take, it was specifically drug arrest data, so you take drug arrest data and you give it to the algorithm and then you send the police out to that neighborhood, right? Based on some rate, they then discover more drug crime potentially in that neighborhood, they feed it back into that algorithm, and what they found, pictured here on the right, is that essentially the algorithm very quickly zeroed in on a small number of places to go back to, right? So specifically those highlighted red areas are the projection over the course of a year of how many times the police would be sent back to the same neighborhood. And the very red ones are they're sent back more than 300 days out of the year, right? So essentially they're just always going back to the same few neighborhoods. On the other hand, on the left, based on health survey data, is where they found actual drug usage was across Oakland, which is of course everywhere, right? And so what this algorithm is doing is just repeatedly sending the police back to the same place, even though perhaps the police should be exploring more widely across the city. And in my own work, I've been interested in trying to understand how does this happen, right? What's the mechanism by which this happens? And for that, I have a thought experiment. So suppose that you have an urn, right, a large bucket, and you have two neighborhoods that you're trying to decide if you send police to. You can imagine these as balls of different colors that you're putting in the urn. Okay? So you'll start off with your historical arrest data, right? So maybe historically you've sent police to one of those neighborhoods 70% of the time and the other neighborhood 30% of the time, right? So now you have an urn that's, say, 70% red and 30% blue. Okay? You decide which neighborhood to go to by reaching in, picking out a ball, and seeing what color it is. You go to that neighborhood. When you go to that neighborhood, you potentially arrest somebody and you put another ball into the urn, right? What you're going to find is that the urn is just going to skew to whichever neighborhood you just keep going to, right? Because eventually you keep going to that neighborhood with the blue ball, you keep adding a blue ball, you add another blue ball, you add another blue ball, right? That increases your likelihood of drawing out a blue ball, so you add another blue ball, and so on, right? Eventually, you just only send police to that one neighborhood. And I would claim that in terms of fairness, that's not really our goal, right? I would claim that the goal should be to actually have the police going to the neighborhood in proportion to the amount of relative crime in the two neighborhoods, right? And really what you've done here is you've forgotten to correct for your sampling bias, right? You chose to go to that neighborhood, thus including some sampling bias, so you have to actually correct for the fact that you chose to go there. The other problem that you had is that your original data included some amount of human bias, right? It's not necessarily a true snapshot of where crime is, it's just a snapshot of where the police have previously arrested people. And in the STS literature, this is a well-known phenomena. And in fact, it's much more complicated than the sort of simplified version that computer scientists have decided to model. Because there's a number of subtle issues here, right? So one is the issue just that your actions may determine then the machine's actions in the future. But the other is, of course, that humans are going to adapt to the system. So in the little story I just told you about how crime works between these two neighborhoods, I didn't include the fact that if a whole bunch of police start going to one neighborhood, maybe crime goes down in that neighborhood, right? Or maybe people just move their activities to another neighborhood, right? You know, humans, right, and make responses to that. And it also doesn't include the danger of introducing technology into a system because it may then be used in a way you didn't mean for it to be. So Compass, the risk assessment tool I showed you at the beginning, was actually originally part of a system that was designed to get people help when they were being released, right? To predict if inmates who are released might need access to social programs, right? To rehab facilities. And so even if these systems were designed with the best of intentions, they may then be taken and used in ways that are really inappropriate to that original use. And then finally, of course, there's the recognition that technology might not be the answer to everything in our society, right? And my co-authors and I originally jokingly called this the Elon Musk trap because he's been in the news recently for coming up with inventive solutions that may not be fully necessary, right? More seriously, there's also been some pushback against the use of risk assessments in many of these settings at all. So this is a statement by, I think, over 100 civil rights groups saying that, you know, we recognize that in some scenarios, risk assessments are already being used and the ship has sailed, but we really want to make it clear that, in fact, we should be weighing these concerns against the values that we care about, right? And this is why I think this is an appropriate thing to consider, obviously, at an ethics symposium. And so one of the things that they bring up is that if the goal is to end money bail entirely, right, we don't need to do that via a risk assessment system. We could look at what happens if you decide to end money bail for anyone convicted of a nonviolent offense. And that's a very clear rule, it's right, it's a policy that could be applied. And from talking to folks who have started to think about this analysis, it looks like even that simple rule is about as accurate as some of these automated tools, right? In which case, why use these more complicated vehicles? And that actually leads us into what we could do to try to avoid some of these traps, right? So I already sort of talked about that first point. So taking these in reverse order, we need to think about whether we need a solution at all. And in this case, we could just eliminate money bail. If we decide that we're not going to do that, so for example, Pennsylvania as a state has mandated that risk assessments be introduced, so we can't just entirely take them off the table, but certainly we should at a minimum do some pilot studies, be very clear about what our goals are up front, because if you aren't, how can you do a pilot study and determine if it worked, right? And then we should also try to create what are known as interpretable models. These are models that you could actually show to the judge. So you don't just have to show to the judge, okay, here's a big red bar, right? This person is scary. You can actually say, you know, the way that I made my decision is if the person was over this age and had committed at least 3 prior offenses, then I said they were this risky. If the person had been in prison for this amount of time and so on, right? You can give them a set of clear rules that they can then look at, and then they can use their understanding of the situation, because remember, the judge makes the final decision, to try to understand how to interpret that. You could also allow the defense to challenge that, right? As soon as you no longer make these proprietary black box models, then some of the human systems that are already in place can actually kick in and be used. It also means that we need to be careful about off-the-shelf methods, right? So for risk assessments, a lot of these are being peddled by companies to various jurisdictions. They may have been trained on data from other jurisdictions. There's a reasonable question about whether they're going to retrain it. Are they going to maintain it, right? Are they going to make sure that as a community changes, the tool changes with it, and so on? And then finally, we need to make sure that these systems that we're using are actually even trying to measure the thing that we need them to measure. If we care about dangerousness, we should be trying to measure that and not whether someone happened to be in a community which caused them to be rearrested. We should also be concerned about what happens with the humans in the loop, right? Are the humans in the loop supporting a fair system? Are they subverting it? And what happens there? So overall, I would say the takeaways of you know, the argument with my colleagues, but also hopefully the takeaways for you, is to value the process over implementing a quick solution, and specifically to focus on the societal context that you are implementing a technological solution within, and understand that that context is not static, right? It may change in response to what you are doing. Thank you, and I'd be happy to take questions. I think there's someone with a question back there.
Dr. Friedler, we've had very blatant examples of bias in mapping systems, such as redlining, which was a federal guideline to banks that's been explored. And that's kind of obvious because they would then classify, without any machine learning whatsoever, certain areas of Philadelphia as being acceptable to loan or not being acceptable to loan. So it seems like we made some progress in terms of not being so blatantly racist. But I wonder if we go back to the roots, if we go back to the original idea behind algorithms that literally were written in stone and pen with Knuth, where they were just simply looking to extend the area. So if you were looking at an algorithm that just said, hey, we've got washed over here, we can't figure out where your land is, and based on the data that we do have, we can extrapolate that your boundary points of B and C when you know A and B will let you put those boundaries back in place. So for redrawing maps, like in the PretPoll example, I can see why the medical data gave a different answer than the policing data. I like how you did that. It's very nice.
So let me respond to a couple of things in there. So there's I guess I would say, like, perhaps we have moved beyond codifying it in our laws, perhaps. I'm not totally sure I'm willing to see that point, but even so, actually, the history of redlining specifically shows up in a lot of these algorithms. So a couple of years ago, Amazon rolled out the same-day delivery service, and Bloomberg News did a whole story about analyzing the specific neighborhoods that these were rolled out to, and found that disproportionately the white customers received this new same-day delivery service, and the black customers in the same cities that were already being served for the white customers did not receive it. They rolled it out sort of by zip code. And Amazon's response was at first to say that they had used an algorithm. This was not bias purposefully, and that specifically their algorithm had tried to take into account like distance to the warehouse, number of prime customers in the neighborhood, I don't know, some other things, traffic, whatever. And then actually pretty quickly there was a lot of public outcry, including from some of the congressmen of the underserved districts, right? And pretty quickly they reversed it, right? But you might say, well, how did it happen in the first place? And I would argue that it happened in the first place because of this history of redlining still existing in our cities today. Other questions?
I might be totally off base, but I always thought that machine learning and algorithms don't go along together. I mean, algorithms is a form of modeling, right? An a priori modeling, just like the two equations that you have. So somebody says, well, a crime rate looks to me like aftershocks from an earthquake, so I'm going to put this in. On the other hand, machine learning is the machine is supposed to learn on the basis of data only, with no formula put in, and just wait and see what happens, what it does with the data. Could you address that issue?
Yeah. So what's actually going on is some nice branding that has made you think that these things are fundamentally different, right? But they're not actually fundamentally different. So a simple example of machine learning is just a linear regression, which might also be known as line of best fit, right? And what you say is the algorithm you are going to use is line of best fit. And here is your data. And then the specific model that comes out the other side is the specific line that it's drawn, right? So it's perhaps a language thing that's a little confusing here, right? The algorithm is the decision to use a line, right? The resulting model is based on the trained data and is the actual line, right? But these systems, really importantly, do not determine on their own whether to draw a line or whether to draw a curve or whether to draw something more complex, right? That's a decision that we, the designers, make.
Hi, Angel Mastercola. First, a quick comment. It seems like there's almost unpredictable reaction between human behavior and assessment and the data-based risk assessment algorithms. I could go into that further, but I just want to transition over to a question. If ultimately we believe that humans are supposed to be the ones that should be making the ultimate judges, maybe helped with the proper usage of these tools, I'm wondering if you could address the question about the application or the situation of gerrymandering and redistricting, which are defined intentionally by humans using machines and data.
Yeah, so I actually have lots of thoughts on this topic. I'm not totally sure where to start.
Just a small question.
Yeah. So I guess what I will say is that I think that, so I in fact have a recent paper thinking about algorithmic ways to do sort of, fair division into districts. Right? And despite that, right, so despite having been one of the people who suggested a way to do fair division into districts, I think I still see that as only the input into a human process, right? I see these various algorithmic ways of generating possible solutions to fair redistricting as being possible suggestions that humans can then consider and assess. Right? And there have been a number of metrics suggested. I would say the most prominent one right now is the efficiency gap, to try to think about whether the suggestions, right, to try to determine how to evaluate the different suggestions in terms of the potential political bias that those suggestions might cause. But yes, I would still say that I don't think that there is a single algorithm out there that's like the correct way to create new districts. This is an inherently complex and human process, as with many of the other algorithms that I've been talking about.
So my question for you is that coming up soon in the 2020, we have the U.S. Census. So what are your thoughts on how now they're thinking about adding the question of basically legal, like basically your immigration status in America, and how that's going to affect all these algorithms basing off of his question about gerrymandering and how that's going to affect our political systems to date, and how that is also going to affect how we, our government systems, like the U.S. House of Representatives, and how it was based on population in the Senate there. So how do you think these algorithms are going to be played in effect in the next upcoming election?
Yeah, it's a huge issue. So I mean, as you were hopefully getting a sense of from this talk, the data that you put into a system has a huge impact on what comes out, right? And so if a large group of people are vastly undercounted, right, because of this new question that they're thinking about introducing, then what that will mean is that all of the potential algorithms that are built up on top of that won't represent those folks, right, and may lead to, you know, further lack of representation in other avenues. Yeah, I think it's really concerning. It's the process, right?
Thank you. My question is about when these companies that are getting into data science more and more in hiring process and things like that, how are they, it's almost like who's watching the watchers? How are companies making these decisions? You know, do they need a chief ethics officer? Almost a position like that? Do you want a data scientist in charge of these things? Just an example, I'm in hiring, and you know, people want their salespeople to be tall, studly beefcakes and babes. You know, is that really a fair thing? But you know, it's a bias that exists. So who do you think should decide that in companies?
Yeah, so there have been a bunch of really good proposals for how this should happen, again, as a process, right? So what you're going to hear me say over and over again is, what's the solution? Oh, I want a good process. And so one of the ideas that's been suggested, it's come under a couple of different names, social impact statements, algorithmic impact statements, that type of thing, is essentially, you can think of an environmental impact assessment. Right? So the idea is that before one of these systems is instituted inside a company or in society, there should be an actual assessment done, right, that generates, you know, paperwork and responds to specific questions about you know, what the training data was that went into it, what assessments have been done to verify that the system is working, what the avenues for redress are when the system doesn't work, because all of these systems will make errors, right? And so what is the process by which you can fix the errors? I think there's also a really important question about who is responsible when they do make errors, right? Again, it's when, not if. So when they do make errors, who is responsible for that? There's a really interesting theory about moral crumple zones put forward by Madeline Ellish at Data and Society that essentially describes the way that, so if cars have crumple zones, right, that are designed so that when you hit something, you're okay, but the front end of your car is not. A lot of these systems, she's suggesting, may start to have human crumple zones that are essentially the person who is designed to be the liability sponge in the system for when it goes wrong. Right? Because of course, you know, the large companies don't want to be the liability sponge, so they'll say, you know, this was never meant to be a final decision. You were supposed to have a human press the button, so that they would be responsible, right? And so I think that you know, I want to see genuine discussion going on. I want to see genuine responsibility that, you know, rests with the people who actually have the capability to overturn a decision or design a new system, right? So I guess my answer to your question is process, right? I want not just like a chief ethics officer who comes in like once a quarter to be like, you guys are doing great, but actually people who are, you know, at the table trying to answer a long series of questions and thinking about those questions all the time.
We have time for one last question.
Hi.
Hi, Sorelle. Thank you so much for this. First of all, making an abstract conversation really tangible. So my question is about, are there cases where there was all this data and there's an algorithm used on similar data elsewhere and it was successful, and then people tried to use that algorithm on this other data set and realized, based on the kinds of things you articulated, not a good idea, and stopped doing it, first of all, and two, wrote about it so that others know that there is a process, and in the process, one of the acceptable outcomes is stop or not to use the data as opposed to just forging ahead and putting the thing in motion, and after the implementation, you realize, wait, there's bias here.
I wish that I could point to a beautiful case study to give you there. I think the closest thing that I've seen to this is so Jigsaw is a company under Alphabet, right, which is the holding company for Google. So Jigsaw thinks a lot about how to automatically detect hateful speech online. And so they have actually been pretty transparent in thinking through how they detect that, and have some Wikipedia pages that they've set up that sort of outline the process that they've gone through when implementing models. So I believe that they implemented a model and then they found that it found statements of identity to sometimes be hateful speech, right? So somebody saying, I am gay, would be seen as using gay potentially in a negative way. And so they pretty transparently highlighted that they had that issue and then talked about what they'd been trying to do to solve that, which I thought was a great example of engaging with these questions in a responsible manner. Thank you, everybody.